What's new in Simcenter 3D version 2019.1? The first thing that's new is our versioning scheme. Our previous production release was version 12. Instead of version 13, we've based our numbering scheme on the year in which the version was released. We've introduced a number of new capabilities. We'll begin by taking a look at what's new in the engineering desktop. In the engineering desktop, we've introduced a number of new enhancements in the area of mesh quality, as well as making connections and post-processing. We'll begin by taking a look at what's new with mesh quality. Here you can see some of the enhancements where we have taken a different approach to capturing the intent behind the geometry in how we abstract the mesh. So we're better able to capture things like bead line and also stamp depressions. Here you can see how we've improved the element quality. On the right you can see elements that are colored red that violate element quality thresholds, and on the right and the left those elements in yellow that only have exceeded the warning thresholds. You can see how the element quality has been improved in the new release. We've also added improved capabilities for support for additive manufacturing. In an additive manufacturing workflow where you would go through a topology optimization to arrive at a shape which you could make in an additive manufacturing process, it has been a challenge in earlier versions in order to mesh that convergent body that results from the topology optimization. For 2019.1, we're leveraging the meshing technology from STAR to be able to quickly and easily mesh the part. It's also been a challenge to mesh parts that have a lattice. This lattice structure can be meshed as a beam mesh and then connected into the existing body using a new command, 1D mesh to face. One very powerful characteristic of Simcenter is its ability to remain associated to the geometry to which loads, boundary conditions, and meshes have been assigned. If the geometry changes, the loads, boundary condition, and mesh will update. This characteristic is called a recipe, and we've expanded the capability of selection recipes to improve and expand the ability to associate selections to the model. And the first is with our input filter. This can now be used to select either polygon bodies or FEM components. We've also expanded it in the area of stacking the selection recipes so that you can combine selection recipes to make a new selection recipe, such as combining one that combines both an attribute and certain specific polygon faces. We can also create selection recipes with bounding volumes, and those can be stacked as well. So in using selection recipes, we can create a template FEM which would be able to select certain bodies with certain attributes in order to create certain meshes on those bodies, as well as certain loads on certain edges or faces based on attributes or bounding volumes. So here we have an example of a template FEM part, which you can see has selection recipes already defined in it. And this template FEM also has no geometry. It's just an empty FEM part which has selection recipes defined that call or look for specific attributes and then it can use those attributes in selecting which bodies to mesh. So here you can see it's using a selection recipe that's been defined in the template fem in order to define which parts to mesh, as well as mesh controls and bolted connections using the universal connection. So we'll go ahead and close that template fem, and we'll use it on some geometry. So here we'll go ahead and open up a part file that has attributes already assigned to the sheet bodies. Here you can see the attributes that are assigned to the sheet bodies, which will be used in the template fem in order to specify mesh parameters. Then you can also see on some of the curves here that we have attributes also assigned that will be used for defining the bolted connections. So next we'll go ahead and create a new fem, and we'll be careful to select the template fem that we were just taking a look at. Also, because we need those curves, we'll make sure we include those in the objects to bring into the fem, and you can see that those bolts have already been created, as well as the mesh, automatically based on those selection recipes. So here we'll go ahead and hide that bolted connection recipe, and then we'll go ahead and specify what elements we want to use to create it. So that greatly simplifies the process to create a finite element model leveraging selection recipes. We're also introducing a new crimp and cinch connection to the universal connections capabilities as an alternative to spot weld for sheet metal assemblies. In the following shell assembly example, we'll take a look at some of the possibilities for automation with selection recipes and universal connections. Here we have some automation that's built around creating selection recipes based on attributes. There's a number of points that define connections, and here you can see the selection recipes that were created through the automation that define how the connection is to be made and between which components in the assembly. And then we also have some automation built around the actual creation of that connection using universal connections. And that will leverage the selection recipes that were defined in the previous step. So now if we take a close look at one of the universal connections, here you can see all of those universal connections that were created automatically. You can see all of the parameters have been specified. All that's left is to define what elements we'd like to use for completing that universal connection. So here you can see the C-hexa shank element with the RBE3 spiders. All right, in support of our solution 402, which is the multi-step nonlinear kinematics, we have a number of joints which makes specifying the kinematic connections very quick and easy so that you can very quickly develop your solution 402 model. The mesh name can now be inherited from the name of the polygon body. This makes it easier to identify which meshes go with which bodies. One new capability in post-processing that's particularly helpful when working with large results is the ability to cache results so that you can easily and quickly open them and switch between different result types. We now have some new spacing options when defining the color bar in the legend, we can specify either a level increment or a round off. We can now make simple distance measurements in post-processing between nodes. One thing to keep in mind, if you want to get the actual distance, you need to select a 1x absolute deformed scale in order to get the correct answer. Have you ever wondered if your finite element model was in sync with your results? Well, now you can confirm that with the new register and verify results commands. Now let's take a look at these new capabilities in the software. In order to enable a number of these new capabilities, we'll need to start in customer defaults and make sure that we turn those on. They're all under customer defaults simulation pre-post. The first is under meshing general, where we can say that we want to use the polygon body names for the 3D meshes, and this works particularly well if you also have turned on under pre-post general FE model create assign assembly component names for polygon bodies. So this will complete the workflow. That particular command is not new, but is helpful to have it turned on. And the last one for results registration and verification, we'll also need to turn that one on under the Solution tab. So here you can see the polygon bodies have names that are assigned that come from the actual component names, and if there's more than one component name or more than one body in a particular component, you can see how that name has been incremented. And the same thing with the meshes on those bodies. Here you can see those names have propagated to the meshes as well. All right, so we've already assigned loads and constraints, and we've run the solution. Next, what we'll do is we'll go ahead and register that result file, because we know that the model is in sync at this stage. And here we can then also verify that those results are still in sync with our model. Next, we'll go ahead and take a look at caching results. And the two result types that we're most interested in taking a look at are displacement and stress. We'll go ahead and cache both of those, so that way it'll be very quick and easy to switch between the two. This is a relatively small model, but with larger models the advantage will be much greater. So here you can see our displacement results. Let's say we'd like to take a simple distance measurement between a few of the nodes. Here's our new measure simple distance in post. We're going to say use deformed coordinates, and we're going to pick a couple of nodes. And one thing you'll notice, if we actually look at the number that we're getting, which is 0.24 for a distance between the two, if we compare that to the undeformed coordinates, which would be the actual distance between those nodes without any loads or boundary conditions assigned, we can see that it's 0.4, and that distance of 0.15 is much greater than the maximum displacement of 1 mil. And that number is wrong. So in order to get the right answer, we need to change our scale to 1x absolute, and then when we take our distance measurement, we'll see that we get the correct distance between the deformed coordinates. So here we can compare 0.4069 to 0.4078, and we can see that that looks much more reasonable compared to our max displacement. We can also take a look at the results in the info window as well. Here we can see the coordinates for the nodes as well as the distance. All right, so let's go to our stress results next, and we'll turn on our annotations to see where our max is occurring. Let's make sure we're looking at an average result as well. So we'll turn on nodal averaging. So now here you can see what node our max is at, and we can go and make a cut plane right through that node by putting in its value. So we'll say cut by node, and we'll select that node by its ID. All right, and there we can see cutting plane right on where the max stress resides. And in the model that remains, we can see where the max is not including that node. All right, next we'll take a look at the level control in our legend in the color bar. So we'll go into Edit Post View and Legend, and here you can see we have a new pull down for spacing. Equally spaced is the existing spacing. If we want, we can round off, or we can select a level increment. However, we have to be careful to select an increment per level that is reasonable in order to get some good results. So let's go ahead and put in something a little bit larger, as this value was left over from displacement. And there you can see the level increments. All right, so lastly, let's go ahead and make a CAD change and see how our results registration and verification are affected. So here you can see our results are still verifiable. Next, we'll go ahead and make a CAD change. We'll use the synchronous move face to do that change. Now here we can see our finite element model has been updated. We'll go ahead and update the mesh to conform to it, and then we can go and verify our results. You can see they're still registered, but here we'll go ahead and verify, and we can see that the verification was not successful because the input file is not consistent with the input file that was registered. And that concludes the demonstration.